the two more things I have to show you are both under this heading of compound functions, which is when we have a function of a function, which is the whole idea of inverses, right? You remember we looked at this, we said, I'll do it the other way around. By definition, if there's some function f and some inverse, f inverse, then if you take the function of the inverse, you should get back your original value, okay? This would be true for all values of x if your inverse existed for all values of x. But you can see with these guys, we've had to do like tricky things with the domain restrictions, right? So let's have a look at these. Make sure I get my order right. Okay, we're gonna do all at once sine of sine inverse, then we're gonna do cos of cos inverse, and then we're gonna do tan of tan inverse, okay? So let's think about each of these. What we are expecting is something like this, right? The sine and the sine inverse, they sort of ought to cancel each other out. But what we're going to do is watch for the range restrictions and domain restrictions that come with each one, okay? So for instance, have a look at sine inverse of x first, okay? Because you always got to go start from the inside and then you can go out. What's the domain restriction on sine inverse of x? We just kind of stated it over here. It's -1 to 1, right? Okay, so therefore, if I put in 2 or 100 or -15, sine inverse is just going to say, forget it, go home. I don't exist outside there because the amplitude of sine has restricted me here, right? So therefore, this whole thing is going to be equal to this, but only in here. Does that make sense? So in other words, I can say this is equal to x in this restricted domain, -1 to 1. Okay, so this is a really easy graph to draw. This is nice. It doesn't even need to be very large. Draw yourself up a nice square set of axes. And I know what this looks like, and I just want to draw this part of that graph. So it's going to look very simply like that. That's what y equals x looks like, but it has a start and it has an end. Okay, that's all there is to it. Okay. When we go to cos inverse, how is this different and how is it similar? Maybe I should ask the question, how is it similar first? What ways are similar? What things are similar? It's still going to be equal to x because you're still compounding the same kind of function and its inverse, right? So I'm still expecting something like this. What else is similar?
Same domain.
Very good, same domain restriction. This thing still only exists from -1 to 1. You can see it, it's my green graph over there. So therefore, the same restriction is true. So therefore, this is also true. Okay? So in fact, going from here to here, nothing has changed. Okay? That seems a bit weird, but just for the sake of completeness, and because it won't take you very long, let's draw this graph. Because it will help set up for us and appreciate the fact that something else is happening here. So let's just quickly draw this segment. Okay, we do it one more time, right? What's the same and what's different? What's the same? 3 times, right? I've been doing this. I've done it again and again and again. It's the composite of one function and its inverse. So I'm expecting that this should look like x, right? But at last, I've hit a difference, right? Because this guy, yeah, is different to these. I can accept any value of x you like, right? Because you guys remember, the graph, it looks like this, right? And crucially, it's got its arrows. It's happy to go as far as you like, right? So therefore, because this exists for all real values of x, therefore, this also exists. Done. And because there's no restriction, I don't need to say anything. Okay? So that was the simplest graph in the hardest topic ever. This guy is just a regular graph, y equals x with no modification. Okay.